All right, so hi everyone. Returning back to part 4 of Zero Knowledge SNARKs. Our recap is going to get longer and longer every week. So we'll try to be faster and faster about our recaps. So again, we'll recap how we defined a SNARK today. We're going to recap the applications that we talked about with SNARKs, and then we're going to get to the actual exercise of building one. So recall that a SNARK stands for a zero knowledge, succinct to non-interactive argument of knowledge. Here again, we've been talking about like knowledge as two sets of information, a public set of information, X, and a private set of information, witness, W, that are different in the sense that the public information can be known by anybody, but the private witness should be protected. And there's two parties. There's a prover who knows both of these, and there's a verifier who only knows the public information. And then the argument part of this whole thing is that the prover wants to prove to the verifier that they know the witness that is private. And formally, they want to prove something about the witness, which is that they know a witness such that there's an arithmetic circuit C, which takes as input the public information and the private information and outputs a 0. So if the prover knows such a witness such that this circuit evaluates to 0, then the verifier should approve them. Otherwise, the verifier should reject them. And we had this structure here where we looked at it where the prover takes his input, the public information, and the private information, spits out a proof, which is a string, to the verifier, which takes his input, the public information, and decides, is this proof enough to make me believe that the prover knows a witness such that that arithmetic circuit C would evaluate to 0? And if so, then they accept, otherwise they reject. And then we also introduced a third party, besides the prover and the verifier, the setup. The setup, which produces some randomness. Some randomness is set up for the prover and for the verifier and sends those pieces of information to each of them. And then the two properties we said that they had to satisfy, one is completeness, meaning that if the prover does know a valid witness such that the circuit evaluates to 0, then the verifier, when receiving such a witness, receiving such a proof from the prover, should always output yes. And then the opposite would be if the prover does not know a valid witness and comes up with a random one like a W star, then the probability that the verifier approves this invalid proof pi star should be very negligible probability, so very small epsilon. And then the succinct part was some runtime requirements that we had gone through last time, runtime requirements that bound how long the prover has to run to generate the proof, how long the proof can be, how long the verifier can run to generate the proof. And we talked about why submitting a proof that is exactly the private witness is not going to produce a valid SNARK. The reason that just submitting the witness as proof is not going to result in a valid SNARK is because this third runtime requirement is not satisfied. The verifier ends up having to run in linear time in the size of the circuit because it has to plug the W and the X in and compute all the operations in the circuit. And we want the verifier to run in a lot less time than that. We want it to run in log the size of the circuit. And then finally, we talked about the zero knowledge part, which is just that a SNARK is zero knowledge if the proof pi reveals nothing about the witness, so that the verifier cannot infer anything about what the witness could or could not be based on the proof handed to it. And we talked about how it's pretty easy to turn a SNARK into a ZK SNARK by injecting more randomness. And the difficult part of building a SNARK is really the succinct property. We're going to see that in action today. So after that, we went and talked about several applications. We talked about rollups, which are a way that zero knowledge proofs are able to increase the bandwidth of transactions on by introducing a rollup server. We also talked about, I'm just clicking through all of these, confidential transactions, where we want to guarantee privacy in the amounts transacted, but it's okay for all the parties in the transaction to be public. So we would replace all the amounts in our transactions with commitments. So these are cryptographic commitments strings, such that a transaction that before had numbers like 10 and 1 and 9 in it would now have commitment 1, commitment 2, and commitment 3 in it. So somebody, a third party viewing this transaction would have no idea what number came from 2 sigma, what number is coming to me, what number is going back to 2 sigma. And we use the zero knowledge proof to help the miners check that this transaction is valid without being able to see the numbers for themselves. So that zero knowledge proof would allow the miner to check that the 10 over here is equal to the 1 plus the 9 without knowing 10, 1, and 9. And we talked about Pedersen commitments as an additively homomorphic example, which allows us to do the check partially without a SNARK because they have a good additive property. And then finally, we move on to the two more exciting examples. The third one being Zcash, where we want to protect the amounts being transacted as well as the identities of the parties. So this requires the concepts of shielded addresses and shielded transaction outputs, so that now going from a confidential transaction to a fully anonymous transaction, you would not even know who the parties were involved. You would not be able to see their addresses. They're shielded. And if you want one such recipient to be public, to be transparent, you could specify it that way so that the address is revealed and the value is explicitly represented. And so in this case, we had to generate a more sophisticated zero-knowledge SNARK so that in particular, we are able to guarantee that there is a valid generation of what's called a coin being some hash of private information from the sender and some randomness and the value that the sender wants to send. And the coins are nullified by nullifiers, which are other hashes of the private information of the, in this case, the recipient, I think, the recipient and other randomness. So Zcash, after all of this, is able to produce transactions that give a third-party observer no clue when a coin has been spent. So a coin could be generated, but once the coin is spent, nobody knows because they can't link a nullifier to any coin. And so that way, nobody knows who has spent money, how much money they spent, and when they spent it. And the last application is Tornado Cash, which is a ZK SNARK-based mixer, so that it's not an entire blockchain like Zcash that is anonymous, but rather it is one smart contract on Ethereum that is anonymous, but it allows some mixing of your tokens based on this architecture on the right here that follows the same logic as Zcash with the concept of the coins and then the nullifiers. All right, so I hope everybody has felt comfortable with the application so far and feel like we have sufficient premises to feel like SNARKs are worth building. If at this point you are not yet convinced, then I'm sorry. But if you feel like these uses of zero-knowledge SNARKs are powerful enough, then let's dive into how exactly to build a SNARK. This one's going to be a very long journey. It's going to be very mathematically intense. So be sure you have a copy of the slides next to your Zoom so that you can refer back to slides that I've already gone through if you need to look at something again. So the first thing we're going to do in building a SNARK is we're going to build the Killian SNARK. Killian SNARK was invented by Killian in 1992, and it's a very simple, but it's a very inefficient SNARK. So no applications today use the Killian SNARK, but it's the easiest to conceptually understand and the easiest to build. What we're going to start with is an argument of knowledge that is not yet succinct or non-interactive yet. Then we're going to turn it into a succinct argument of knowledge that's still interactive. And then finally, we're going to turn that into a fully non-interactive succinct argument of knowledge, which will be a SNARK. And here, just as a recap, remember we have these three parties to set up, the prover and the verifier, and they must satisfy the completeness and the proof of knowledge properties. And we can imagine in our heads that the diagram of the structure and the flow of information looks like this. So that's the roadmap for today. Let's start with defining a very, very important theorem. A PCP theorem, also known as the probabilistically checkable proof theorem, is not something we're going to prove today, but we're going to use very heavily today. The theorem says that for all circuits, all arithmetic circuits that take as input public information and private witnesses, there always exists a proof system composed of the setup, prover, and verifier, where number one, the prover will do the first step of generating some proof. We're not saying what exactly that proof is yet, but generating some proof with size linear in the size of the circuit. So the proof size is the size of the circuit raised to some power slightly bigger than 1. The prover can generate this proof in linear time in the size of the circuit, and that prover can send that proof to the verifier. We're saying for any such circuit, this can always be done. That's the first step. The second step is the verifier then has this proof in their hands, but the verifier does not look at the proof itself. The verifier queries some number of random bits from the proof. They choose, there is a constant that's predefined, lambda, and the verifier queries some number of random bits that is linear in lambda from the proof. And the querying and the parsing total for the verifier takes time, linear in x, which is public information, and linear in the log of the size of the circuit, because again, lambda is a constant, so we can say that this is linear. That's the second step. So the verifier is now sort of spot checking the proof at some number of random points. And then if the prover has been honest in generating the proof, then each of these spot checked random bits from the proof will appear correct to the verifier. Otherwise, if the prover has been dishonest, then with 50% chance, the verifier will notice that any random bit that they check is wrong. Because again, bits are either 0 or 1. So if it's the bit the verifier expects, then it'll deem it correct. If the bit is not what the verifier expects, then it'll say that the proof is invalid. So then the verifier accepts this proof if all of the bits that it has spot checked, all these random bits, are correct. This is the basic PCP theorem. It's saying that for no matter what you're trying to build with your circuit, no matter what you're trying to check with your SNARK, you could always come up with a prover that creates a proof with these properties, and where the verifier just has to spot check some number of them. And then if the prover has been honest, each of these spot checks will be correct. This gives us one result, which is that if the prover has been honest, the verifier should always accept, because if the prover is honest, then every spot check will return correct. Otherwise, the verifier will accept erroneously. So if the prover has been dishonest, the verifier might be tricked into accepting, but only with probability 1/2 raised to the lambda power. So that probability goes towards 0 if the constant lambda chosen is big enough. And a typical constant for lambda is like 8. So like 1/2 to the 8th power is pretty close to 0. A diagram for this PCP theorem setup for the proof is that the prover will take in as input, again, the public information and the witness. It'll generate this proof, a long proof, because it's linear in the size of the circuit. But then the verifier will only read some constant number of bits from the proof. So it's not reading the whole proof, and it's only spot checking, and then it'll output either it accepts or rejects. Questions about the PCP theorem?
Yeah, Bill, for the prover part, like you said, this is linear in the size of the circuit. Is that because like epsilon is like can be sufficiently small for it to be basically
That's
linear?
right. Yeah,
Okay.
so epsilon is always assumed to be sufficiently small, which means that this is essentially linear in the size of the circuit.
So in this case, is epsilon like an error, or like you have to do certain computation to make epsilon smaller?
Epsilon is, I think, a theoretical value that you can prove is smaller than some other like constant or whatever, so that it's like small enough that we don't have to worry about it.
Okay, cool, thank you.
And
yes.
So there's line number 2, verifier queries of lambda random bits. I'm wondering, in terms of the time complexity of x plus lambda log c, why does the log c get into that time complexity? Like, why does the size of c affect how long it takes for the verifier to query?
Yeah, so the reason is the verifier isn't just selecting some random lambdas and then just querying lambda bits. It's querying some linear value in lambda bits. So for each random, bit, each random value that it generates, so it's going to generate lambda of these random values, right? But for each random value, it's going to maybe sample like 2 bits or maybe 3 bits or something from pi, from the proof. But it's going to be linear in the size of lambda. So for each lambda, each of the random bits that it generates is going to go query some constant number of bits from pi, and figuring out what those other bits to spot check are takes like log the size of the circuit sort of compute time for the verifier to figure out. So like,
Okay.
for instance, one way you could think about this is if like each like say your lambda is like 1, that means you're only going to spot check once. The spot check, you could say, generates a random number from 0 to 100. Say the proof is of size 100. But then maybe the actual number of bits you check is always 3. You check the number at that randomly generated bit. You check the number at like that random bit plus 33 index mod 100, and you check the random bit at that bit plus 66 mod 100, so that you like end up checking 3, bits of the proof. But those 3 bits are determined based on one source of randomness. And so in that case, maybe you have to do like something a little bit complex so that it ends up being log the size of the circuit time to, figure out what the random bits are.
So there's something going on there, and it takes a bit log. See, cool. And then for 3, I'm wondering, I guess previously how I thought about things was that like it's not clear to me why the verifier can verify each bit individually from one another, as opposed to like needing to have a full, set of bits to verify it collectively.
So you're saying it's not clear to you why spot checking is sufficient?
Or just how, or I guess I just don't know how it works, like how you can, like, what do you do when you get a bit and verify the single bit? But I guess that's just part of PCP, that there is some V where you can run that.
Yeah, that's right. So that's something that like would get into proving how the PCP theorem works. And we're just going to assume that it works. We're not going to get into specifics of like, how can you guarantee that whatever bits that you've checked, how can you guarantee that they're correct if the prover has been honest?
Yeah, sounds good. Cool, thanks.
Yes, other questions? The one thing that you'll notice is that I highlighted in red the size of the proof. And that's because the way that the proof has been generated right now, it is not succinct, right? Because the proof that we need to generate for a SNARK needs to be log the size of the circuit. And right now it is linear, slightly more than linear. So we're gonna eventually fix that problem. But right now, like, it is still not a SNARK. The proof isn't succinct enough to be a SNARK.
Does it still need to be log the size if you're not gonna check all the bits in the proof? Like, what's the advantage of?
So we're going to talk about why exactly the verifier needs to be sent to the entire proof, even if afterwards the verifier only needs to query some bits of it. We're going to talk about why it's necessary to send the entire proof later. But just think that like the reason why succinctness requires the proof length to be short is because communicating the entire proof to the verifier would be very expensive on the blockchain.
Okay, gotcha. That makes sense, yeah.
All right, so since sending this entire proof to the verifier is too long, and because the verifier is not reading the entire proof, why do we need to send it all if we could just send the bits that the verifier wants to query? The answer to this is a bit adversarial. It is that the prover needs to first commit to a proof. The prover needs to first build the entire string and send the entire string to the verifier before the querying starts. Otherwise, if the verifier is querying one bit at a time from the prover could send random bits back that are not like together forming a correct proof, but that take advantage of the fact that the prover is, every time the verifier is querying, the prover is gaining knowledge about like which indices of the string the verifier is querying. And so the prover could adversarially take advantage of that if it had not already committed yet to a proof. So in that sense, it's sort of like, it's like if the teacher was like, okay, everybody submit your homework. And then the teacher's like, all right, I'm going to spot check just some of the problems on the homework. I'm not going to check every problem on the homework. But the teacher still needs all the students to submit the homework first. Otherwise, if the teacher just goes around and asks students for spot checked answers to the homework, the students could just not do the entire homework and then only do the questions that the teacher is about to spot check. That's sort of like the cheating that the prover can do if the verifier starts querying bits of the proof before the prover commits to the whole thing, before the prover sends the whole thing in for inspection. And if this querying happens without sending the whole proof over or without committing to the proof first, then it's possible for a dishonest prover to convince a verifier to say it's to accept it, even though it does not know a valid witness. That means that we, in the current setup, would have to send the entire proof over, but that means we're not succinct. So how can we make the PCP succinct, given that we can't just send the bits over? The solution is, instead of sending the entire proof over, let's send a, let's first take every single bit in the proof and build a Merkle tree from it. We build a Merkle tree from it and we gain a Merkle root at the top, H. Let's send a Merkle root from the prover to the verifier instead of sending the entire proof, pi. The Merkle root is just like 32 bytes, right? It's very, very short, but it is a commitment to a proof. It means that once we've sent a Merkle root over, the prover cannot modify its proof. Otherwise, if it were to modify its proof, the Merkle root that would come from it would be different from the one that we sent. So that means that it's sort of like sending in like sending in a homework that's encrypted, but like you know that like the hash of the homework assignment, hash of the homework submission is binding, so that like the student cannot change the answers to the homework after they've submitted the homework or something. So only the Merkle root is first sent to the verifier. The verifier will then send over the k, or lambda, k, where k is linear in the size of lambda. It'll send over the k positions of the proof that it wants to open. So it'll query those positions. And then the prover is going to send over those bits, and it's going to send over for each bit the Merkle proof that that bit correctly was positioned in some index of the total proof pi. So as opposed to the original system we had, where we sent the entire proof over, and then when queried, we would send k bits over. Here, we're only sending a root over first, and when queried, we send the k bits, and we send k Merkle proofs. But because each Merkle proof is only log in the size of the proof, it's because it's log in the size of the Merkle tree. In total, we're going to send k times log the size of the circuit amount of information the second time around. So in this way, we've turned a otherwise linear in size of circuit proof and communication load into a log size of the circuit communication load. And so this is acceptable. This would be succinct enough in like communication load. So in this way, we've cleverly used a Merkle tree to commit to our proof without having to send the whole proof over. And then each time we're being asked to open some position of the proof, we just have to send over a Merkle proof that guarantees that the bit that we're sending over was indeed included in the proof that we'd committed to earlier. Questions about this modified protocol that makes the PCP succinct?
Where does the log of the size of the circuit come from?
The log the size of the circuit is the size of the Merkle proof. So size of the Merkle proof for any to prove that any element is positioned in the proof, you have to generate a Merkle proof that is always log in the size of the tree, Merkle tree. And in this case, the size of the Merkle tree is the size of the proof, pi. And the size of the proof pi we said is basically linear in the size of the circuit.
Gotcha.
So it'll be log the size of the circuit. And we have to send k of these Merkle proofs. So it becomes this k times log size circuit.
Great.
One thing I'm trying to understand is this idea of an adversarial prover. And going back to the homework example, it's like if the teacher asks for one specific question and the student is able to answer that question, then it works out. But like that only works for the student if they're actually capable of answering every question, right? And then when prompted for each individual question, they can just answer that one. So it's not about like failing to be able to answer every question. It's just about like not wanting to do the work to answer every question. But so
You're
it's
right.
so like
You're
yeah.
right. So the student teacher example is not like completely accurate. I guess maybe a better way of phrasing the student teacher example is like maybe like when the teacher asks you the first question, like that they're spot checking, it gives you a hint as to what the teacher's second question could be asking. And so you use the answer that you gave in the first question to inform the answer you'll give on the second question and stuff like that. So like maybe on like multiple choice tests, y'all have experienced this where like there are two questions in the test where it's like, well, okay, if I don't actually know which of these two answer choices is right, but I know if I choose answer choice A for question one, I need to choose answer choice B for question two. Like, so the answers that you have to give to these different questions are related. So
Cool.
in the same way, the bits that you have to send back when queried might be related if you know which bits you're being queried for before you have to send the whole proof over.
Got it. Yeah, and so is it right to think about it that, given there's this adversarial prover and the verifier is querying one bit at a time, it's not guaranteed that the malicious prover would be able to pull off faking that they know the witness, but like it increases the chances to much higher than you expect in the system. Is that the right way of thinking about it?
Yeah, that's right. So you give the prover a much better chance of cheating their way to validity if you don't make them commit to a proof first.
Okay, sweet.
Okay, then now we have successfully made the probabilistically checkable proof succinct, but we have another conundrum, which is that it is still interactive. What exactly is a non-interactive proof? It's one where the communication is only one way, where the prover sends something, but the verifier doesn't communicate back to it. Previously, in our previous slide, we just saw that the verifier has to send a bunch of these queries back and forth. So like there's an arrow going from prover to verifier, but then there's an arrow going from verifier to prover, and then back and forth. We want to eliminate all this back and forth because it's expensive on the blockchain. So we need to make it a non-interactive proof where the only arrow is from prover to verifier. So how do we make this PCP non-interactive? The idea is, instead of the verifier generating the random bits, let's have the prover generate the random bits that it's going to send over. Because the only thing that the verifier was sending the prover was the randomness. The verifier comes up with the randomness, and the verifier sends those random bits over to the prover. Why don't we just let the prover generate the random bits? This runs into the exact same problem that Cole was just asking a question about and that we mentioned earlier, which is we can't let the prover generate the random bits because the prover could then change the proof that they're submitting based on the random bits that they're being queried for. So if the prover generates some random bits, it's essentially the same as the verifier asking for the random bits without the prover having sent the proof over yet. So this naive solution to make it non-interactive isn't going to work because it lets the prover cheat. However, there is a clever way to allow the prover to generate the randomness without allowing the prover to cheat. This is called the Fiat-Shamir heuristic. This was invented a long time ago. It is called a heuristic because I don't think it is provably secure, but it is, it's an algorithm that not necessarily always guaranteed to work, but it's a heuristic that you can apply that, at least in all the instances I think that people have tried it, will work. So the Fiat-Shamir heuristic is a way to turn any interactive protocol, this is like a protocol, an interactive protocol into a non-interactive protocol. So for any interactive protocol where the verifier only has to send randomness back to the prover, there exists a non-interactive protocol that replaces the verifier's randomness with the values of a random oracle hash function H. Here I've used random oracle in quotations because random oracle is a stronger requirement than just being collision resistant hash function. For instance, SHA-256 is not a random oracle hash function. SHA-256 is a valid hash function, but not a random oracle. A random oracle hash function has to be provably random across the distribution of possible hash values at the other end. There are lots of random oracle hash functions out there, but let's just assume that we have one in our hand, H. Then any interactive protocol can be made non-interactive. And let's see how we can make this happen. The first step is prover will generate the proof. And then the prover will take the Merkle root of this proof, H, which previously it was going to send to the verifier. Now instead, the prover is going to take that Merkle root and label it message 1. Then the prover will generate some randomness. The way the prover is going to generate the randomness is it's going to take this hash function H, plug in the public information, and plug in this Merkle root. That way the randomness it generates is binding to the Merkle root that I had built before, and thus binding for its proof. If the prover changes its proof later on, after it has seen the randomness, then this relationship will no longer be true. And so by having the prover generate randomness that is reliant on the proof it built in the first place, it forces the prover to have committed to its proof without the prover actually sending it to the verifier yet. Then, after the prover has generated this first random bit, per se, the prover will take the bits that this random bit is querying from its proof. It'll take the bits for those positions are, take their Merkle proofs and label all that information into a string called message2. And then that way, the prover can send the public information X, message1, which is the Merkle root for the proof, and message2, which contains the random bits for these positions R and the Merkle proofs for them, and send all of these pieces of information to the verifier all at once. So this is non-interactive. The verifier doesn't have to send anything back. But crucially, the verifier can check that the randomness the prover used in this process was generated in a way that is binding to the Merkle root of its proof in the first place. So that means that the prover could not have cheated, because if the prover tried to cheat and change the randomness it was using after it had already generated the proof, then when the verifier checks this condition, it's going to be false. This could potentially be done with multiple iterations if the verifier had to communicate with the prover several times. You know, if it was like multi-stage, like in our case, the original protocol had 3 steps of communication: first from prover to verifier, second from verifier to prover, and third from prover back to verifier. If it was instead like 5 steps of communication, the Fiat-Shamir heuristic would still apply. You would just like generate more bits of randomness using the same methodology. Questions about this Fiat-Shamir heuristic? This is the difficult part. I feel like maybe I lost people.
I think looks good to me. You're generating the randomness from the commitment, and then you sort of get locked in. I don't quite see the 5 back and forth way how it work, but I can
Yeah, so
imagine it'd be similar.
the way the 5 back and forth one could work is, so it has generated a message2 that would have sent to the verifier if it were interactive. Message2 is what it would have sent to verifier if it were interactive. Message1 is what it would have sent the verifier if it were interactive. So like message1 is what the first step of communication would have been, and message2 is what the third step of communication would have been, right? So in order to generate the next bit of randomness to send the 5th step of communication over, it would generate that randomness using a hash of, say, the message2. And so the new randomness, like R prime, would be binding to message2 that I had sent before.
Good. Yeah. One other thing I'm thinking about, this was a couple of weeks ago, we were talking about examples of ZK in the real world, like the idea of holding 2 different colored markers behind your back and mixing them up. And we had talked about the idea of turning that into like a non-interactive proof, but we never, and so I was just thinking about that. Maybe the Fiat-Shamir heuristic would apply to that marker example, or maybe not.
Yeah, I think that's definitely possible. I personally didn't like have an answer to that exercise. I don't know exactly how it would turn into something non-interactive, but yeah, I think the Fiat-Shamir heuristic would be a good like thing to try in that direction.
All right, I'll think about it some more and report back next week, hopefully.
Okay. So here's also a diagram for how we have turned our previously interactive protocol into a non-interactive one using the Fiat-Shamir heuristic. So previously we had the prover send message1 to the verifier. The verifier would choose some random bits and send it back. And the prover would take the random bits and generate message2 to send to the verifier. Instead, here we're going to have the prover do all the steps itself, except instead of letting the prover choose whatever random bits it wants, we force the prover to choose random bits that correspond to the random oracle hash function of the public information and the first message it had planned to send. That way, the randomness will not allow the prover to cheat and go back and change message1 after it has generated the randomness. Then from the randomness that it has received from the verifier, received in quotations because it really generated the randomness itself, the prover will then generate message2, and then it'll send all the things over at once to the verifier. And the verifier will check 2 things. It'll check that the randomness was generated correctly using this random oracle hash function, and it'll check the proof itself. And then it'll say accept or reject. So in this way, you see that there is 3 lines over here of communication. Now there's only 1 line in one direction. And so this has become non-interactive. Questions about the Fiat-Shamir heuristic? Okay, so that's the basic steps to building a Killian snark. After having done all these steps, the resulting protocol is non-interactive, it is succinct, and it is an argument of knowledge that has a prover and a verifier. It doesn't actually use any setup, but will generate a proof that gets sent over and can be verified. However, we're not satisfied yet. And so in particular, one thing that this snark is not is it's not efficient yet. Why? This is something that I haven't revealed to y'all yet, but in the Killian snark, the prover has to run in time that is cubic in the size of the circuit. And that is way, 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 way too slow. Given that we had to make it succinct on the proof size and non-interactive, we ended up coming up with a proof that is just way, way, way too, a prover that is way, way, way too slow in generating its proof. That's the first thing that we're unsatisfied with. The second thing that we're unsatisfied with is that it's not zero knowledge. The snark that we just generated is not zero knowledge. And in particular, if we're gonna build a zero knowledge snark, we should take a different avenue towards generating the snarks in particular. So for the last leg of all of these snark talks, the last leg is going to be taking a different route that is not the Killian snark route to building an efficient snark that can be zero knowledge. If you have been following along so far, I very much appreciate it. And I'm going to say that from here on out to the end of this talk on snarks, it is going to be even more mathematically intense than before. But bear with me because this is the part that is actually being used in production in all of these different ZK applications today. So I hope that motivates us to stay locked in on these mathematical theorems and such. To build an efficient ZK snark, the direction that we're going to take is not using the PCP theorem. Instead, we're going to take a lot more steps to build something that is a lot more general. None of these words are going to make sense to you right now, but by the end of this leg of the talk, it's going to make sense. The first step we have to do is that we have to convert our arithmetic circuit C into a rank 1 constrained system program, or R1CS program. The second step is we have to convert this R1CS program into a linear probabilistically checkable proof. Linear PCP is a special form of PCP that is that has some properties we'll talk about later. Then we'll be able to compile this linear PCP into a ZK snark that uses a trusted setup. Now, refresher, what exactly is a snark that uses a trusted setup, if anyone remembers? So a snark, yes, Amy.
Oh, I had a question on the prover running in the O of C cubed. Where did you get the power 3 from?
This is a statistic. I do not have the computations behind it that demonstrate that it runs in this time, because if we're not proving the PCP theorem, we don't end up getting to see how the prover, what steps the prover is taking behind the scenes. So I can't explain to you why it is cubic, but I can tell you that it is cubic.
I see. And for a trusted setup, it's where, like, when you generate the randomness, like, you don't need a trusted third party to generate the randomness. It can just be generated.
Clarify what you're defining here.
ZK snark with trusted setup is where you need a trusted third party to generate the randomness that they give to the prover and the verifier.
Good. Yes. So you need a trusted third party. And why do you need this third party to be trusted? What's wrong if the third party is not trusted and leaks the randomness to everybody?
The prover and verifier can't know each other's randomness.
Yeah, so that's right. This is a SNARK setup. A SNARK setup with a trusted setup is one where the prover cannot get their hands on the randomness handed to the verifier, otherwise the prover will be able to cheat. So like in our previously Killian SNARK, if the prover got their hands on the verifier's randomness, then they could have cheated because they could have generated the proof to do whatever it needed to fulfill the spot checking. So that's an instance where we would have, if we used a setup algorithm, needed it to be trusted, but we had used the fiat-Shamir heuristic so that we could avoid the setup algorithm and just had the prover generate its own randomness. But that's an example where like you do not want to leak the randomness that the verifier is using to the prover. Typically, leaking the prover's randomness to the verifier is not as bad. It could compromise the zero knowledge property of the SNARK though, if the verifier learns of the prover's randomness. But great job recalling that. These are the 3 steps that we would take if we're trying to build a ZK SNARK with a trusted setup, or if we're trying to build a ZK SNARK with a transparent setup. We would instead, for step number 2, convert the R1CS program into a linear interactive Oracle proof, which is a IOP, a linear IOP. And then we would compile the linear IOP into a transparent ZK SNARK. So the last leg of this lecture, which is going to probably spill over into next week, is going to be demonstrating how to do this and demonstrating how to do this. So we end up learning how to build ZK SNARKs with trusted setups and transparent ZK SNARKs. Questions before we begin? All right, let's go. So the first thing we need to do is convert our circuit into a rank 1 constrained system program, R1CS, and then everything else. So let's define what an R1CS program is. An R1CS program is just another way of representing an arithmetic circuit. It's another way to mathematically represent one, and it's reducible to arithmetic circuits. It's like an equivalent way of writing the same thing out, but just in a different format. So remember that our arithmetic circuit has multiplication gates and addition gates in it. For our R1CS program, let's first define A, B, and C as matrices. Matrices from this that draw elements from this finite field that are of size m by n plus 1. We haven't yet said what m and n plus 1 are, but let's just say we define these and let x, that public information, have been drawn from the public information is a vector. Let's say that the vector is of size k, and let's say that the size of the witness w is n minus k. So that way, when we concatenate x and w together, we get n, a vector of size n. So that's how we've defined n. N is just equal to the length of x plus the length of w. Here, the very important assumption is that the size of our finite field, again, finite fields can be just like the integers, the real numbers, lots of finite fields that we're very familiar with. We just need the size of the finite field to be much, much larger than m, which is the other size of the other dimension of these matrices. So then once we have these matrices, if we are taking as input the public information x and the private witness w, this rank 1 constrained system will output 0 if, and here we're defining a couple more things. We're defining z to be a concatenation of the scalar 1, x, and w, so that z, having concatenated all these things together, has length n plus 1. And now we're saying the program will output 0 if the dot product of a and z times the dot product of b and z. This is a, I think this is an element-wise multiplication. This is element-wise multiplication. Is equal to dot product of c and z. If this is true, the program will output 0. And we're going to argue that that is equivalent to generating an arithmetic circuit that evaluates to 0. From here on out, we'll call z the input vector. And a, b, and c are these matrices that are expressing m constraints. We're going to call these rows of the matrices, they're m total rows. We're going to call them all constraints. Here, every arithmetic circuit C where we have public information X and private W such that the arithmetic circuit evaluates to 0. Every such circuit can be written as an R1CS program where we set M to be equal to the number of multiplication gates in C plus 1. So now we've defined what M is and we define what N is. We define what A, B, C, and R, and we already defined what Z is, and now we know how this R1CS program has been set up. The question that's remaining is, okay, how exactly do you turn an arithmetic circuit into an R1CS program? We're going to cover that in a second, but before we get to that, any questions first about how I've defined all the things in this R1CS program lingo? I'm about to show you an example of how to build an R1CS program, but first, any questions about the notation?
Yeah, so I'm just wanted to talk more about the size of F being much bigger than M. So M is the number of multiplication gates in C plus 1, and then A, B, and C are in a field of dimension M times N plus 1. And then the number of elements in F has to be much, much bigger than M.
This requirement is not necessary to I guess, build an R1CS program, but this requirement is necessary for the resulting R1CS program to be secure as part of our SNARK. An intuition for why we need this to be true is that if the size of the field is too small relative to M, then the chance that a dishonest prover can get lucky with like guesses becomes too high for us. The larger the field is relative to the number of constraints, the harder it is for a dishonest prover to get lucky.
Okay, sweet. And do you know like what an example field that would be used might be?
Yeah, so fields could be like the real numbers, and it could be the integers, and it could be a more common example is like the integers modulo some large prime.
Yeah, and then the prime has to be much, much bigger than M, basically.
That's right. Yeah.
Okay.
So now let's talk about an example of an R1CS program. This one is not one that is built from an arithmetic circuit yet. We're going to get to that in a moment. But let's start with trying to build an R1CS program that would accept our X. Let's ignore W for now. Let's just say that there's just a public information X, but no witness yet. Let's build an R1CS program that accepts X if and only if X is less than 2 to the D for some constant D. So let's build an R1CS program that can check whether the X that I have in my hand is smaller than some power of 2. What could we do here? As a tidbit, we could build an arithmetic circuit for this problem. We could build an arithmetic circuit that accepts X if it's less than 2 to the D. The way we could build such an arithmetic circuit is to build the circuit to be this humongous polynomial. X times X minus 1 times X minus 2 times X minus 3, all the way up to X minus 2 to the D minus 1. This arithmetic circuit will evaluate to 0 if X is any of the integers between 0 and 2 to the D. But if X is an integer that is not within 0 and 2 to the D, then this arithmetic circuit will not evaluate to 0. This polynomial will not evaluate to 0. Questions about how we could have represented this problem as an arithmetic circuit? Now, that's not what we're going to do for the R1CS program. The R1CS program, we're going to take a slightly different idea. The way we will try to build an R1CS program with these matrices A, B, and C and stuff for this problem of checking that X is less than some power of 2 is let's try to represent our X as a set of bits, W1 through WD. Each of these W1 through WD is either 0 or 1, such that X can be represented as W1 times 2 to the 0 plus W2 times 2 to the 1 plus W3 times 2 to the 2. So basically, these bits are the binary representation of X, if X is within this range. If there exists such a binary representation such that this equation is true, then that's enough for us to show that X is less than 2 to the D. If X is greater than 2 to the D, or if X is negative, then this representation should fail. So how can we represent this argument using some matrices in our R1CS program? Well, here we have defined D+1 constraints. The first constraint is that this equation must be true. We will slightly reorder this equation so that we take the x and we move it to the left, move it to the right-hand side, so it becomes negative x plus this binary representation times 1 equals 0. This constraint is mathematically equivalent to this equation up here. We just rearranged it a little bit. That's our first constraint. And then the D other constraints that we have is just constraining every one of our variables W1 through WD to be a bit, to be this is either 0 or 1. So we're saying every one of these WIs has to be able to satisfy this equation, which is WI times WI minus 1 must equal 0. If WI is equal to 0 or 1, this will always be true. If WI is not equal to 0 or 1, then this will never be true. So in this way, we've built D+1 constraints over our D+1 inputs. Now, these constraints can then be represented using the matrices A, B, and C, and the input vector Z. In this case, the input vector Z, we will represent as the scalar 1, the public information X, and then these bits W1 through WD. And this will have length D+2 total. So given that there are D+1 of these constraints defined over these D+1 variables, and we have an input vector Z with length D+2, then we can finally build our matrices A, B, and C. These A, B, and C will have dimensions D+1 times D+2, and they will look like this. The first such matrix A is going to have as each of its rows the coefficients in front of all of the inputs, X, W1, WD, etc., that are part of this first constraint. The second row of A is going to be the coefficients for the second constraint. The third row of A is going to be the coefficients on this side for the third constraint, so on and so forth. So let's see how that boils down. For our first constraint, what is the coefficient in front of the scalar 1 that is our input? That coefficient is 0 because 1 does not appear in this term of this equation. All right, what is the coefficient in front of X in our first constraint? The coefficient for X is going to be -1, right? Because it's a negative X over here. So this value will be -1. What is the coefficient for W1 in this term of this first constraint? The coefficient for W1 is 2 to the 0, which is equal to 1. Sorry?
Yeah, I wasn't sure if that was a rhetorical question. I just said 1.
Oh, yes, thanks. And then W2, the coefficient for W2 would be 2. Coefficient for W3 would be 4. And then finally, the coefficient for WD would be 2 to the D minus 1. And so these coefficients together will be the first row of our matrix A. For matrix B, the terms that appear in the first row of matrix B will be equivalent to the coefficients of all these input terms in the second term of this first constraint. The second term here is just a scalar 1. So that means that the only non-zero term in this row of matrix B will be a 1 at the very beginning, because our input, that is the scalar 1, appears and is multiplied by the value 1. So everything else in this row will be 0. And then finally, for C, well, C has an easy job because everything on the right-hand side of all these constraints is a 0. So C can just be a big old matrix of zeros. Questions about how the first constraint has been represented using A, B, and C. This first constraint being represented using A, B, and C. So then we get to the other D constraints. The other D constraints here can be represented a lot more simply than the first one, because all the rest of these D constraints don't use all the inputs. For instance, the second constraint is just that W1 times W1 minus 1 is equal to 0. Here, the row in matrix A should contain all the coefficients of these input terms that appear in the first of the two multiplication terms in this constraint, which is just W1. So the only term in the second row of A that should be non-zero is the term corresponding to W1. And that should have a value of 1 because W1 times 1 is what we see here. For matrix B, the only terms that appear in the second part of this multiplication are the scalar, which is multiplied by -1, so we get a -1 here, and W1, which has a coefficient of 1, so a 1 goes here. Everything else is 0. And moving on through the rest of the constraints, constraint 3, constraint 4, constraint 5, etc. For matrix A, the only terms that are non-zero are always going to be the terms that correspond to the Wi that is being represented, and they'll all be 1s. So this corner of matrix A is going to be an identity matrix. The diagonal of 1s, everything else is 0. And these two columns are going to be 0 throughout the rest of the rows. Matrix B will always have a -1 in its term. So the first column of matrix B for the rest of the rows will always be -1. And then similarly, it will have an identity matrix over here. And so we have successfully turned our problem of showing that like X is within 2 to the D into an R1CS program. So that if the R1CS program evaluates to true, then the integer or finite field element X must be between 0 and 2 to the D. Questions about this example?
Are we?
Yes.
Sorry. Is it gonna always be the case that we'll try to get C to be a 0 matrix, and is it possible that it wouldn't be a 0 matrix?
Yeah. So C, once we get to the ZK SNARK construction, is not going to just be the 0 matrix. But for this simpler example, C could be built to be 0, which makes the problem just a little bit simpler to imagine.
Could you not rearrange things so that C isn't 0?
The key to rearranging things is that we want to always make sure that each of these constraints is rank 1. In order for it to be rank 1, we can only have one big multiplication operation on the left-hand side of every constraint. So we're going to manipulate things such that there's always one multiplication on the left-hand side and no additions after the multiplication has been made.
Okay,
and so sometimes
gotcha.
C will have to be non-zero.
Thanks.
So if we were to do A times Z, element-wise multiplication with B times Z, and check if it is equal to C times Z, this is what that big old equation would look like. This is our matrix A, this is Z, this is our matrix B, that's Z, this is our matrix C, which is just zeros, and that is Z again. And this equation, which now you can see is sort of just like linear algebra for a set of constraints, this equation will be true only if X is between 0 and 2 to the D. That brings us to time. So we'll pick up again next week with, I'm going to show you an example of how to turn an arithmetic circuit into an R1CS program. Then I'm going to tell you how we can generally build a arithmetic circuit into an R1CS program. And then we're going to continue with the rest of the steps, so on and so forth. I'm going to stay for questions, but otherwise, yes, this is the end of the presentation for this week.